Hello, in today's lesson we are going to have a look at redox, but specifically a type of redox titration. We are first of all going to do a quick recap of reduction and oxidation reactions to make sure that everybody is still familiar with them. They are a part of Unit 1 now, which it's been a very long time since we looked at. So hopefully in doing a wee recap of this, it will help you understand if it's something you need to go back and look at or if you're fine with redox. So what we're going to learn today is how to accurately carry out a redox titration. We would usually perform this redox titration in the lab. Obviously, we're not going to do that today. I'm just going to show you a hypothetical titration so that we can calculate the concentration of a reactant. Our success criteria is to understand the process of accurate volumetric analysis. So we're going to look at different types of glassware and hopefully, since you've already carried out titrations before, you are aware of the steps in the process to carry out an accurate titration. So it'll just be tying those two things together. So a wee recap first of all then. What is redox? Well, we have oxidation and reduction. The way to remember what oxidation and reduction are is to use oil rig. So OIL, oxidation is loss of electrons, and RIG, rig, reduction is gain of electrons. So if something's gaining electrons, that's going to be reduction. If something is losing electrons, that's going to be oxidation. So a redox reaction, just to recap, is one where we have reduction and oxidation taking place. You can find the equations for reduction reactions on page 12 of your data booklet, and you simply have to reverse the equation in the opposite direction for it to become the oxidation equation. So I'm just going to talk you through an experiment that you hopefully have all done in class with copper and zinc. Now you start off in this beaker here with a little piece of zinc. So zinc is kind of silver grey in colour, and a blue solution which is copper sulfate. Now what happens between copper and zinc is they switch places. So this is a displacement reaction where we end up with a colourless solution which is zinc sulfate and solid copper. Now, to understand what happens, we can use our electrochemical series to do this. If we have a wee look at page 12 of our data booklet for these two metals, we can see that zinc is above copper in the electrochemical series. So when we come to write the oxidation and reduction equations, then we immediately know that the zinc is going to be oxidized, so we're going to flip that equation, and the copper is going to be reduced. Here are the equations that I was talking about. So the zinc atoms, which are here, are going to give electrons to copper. So it's losing these electrons here, that's what oxidation is, becoming zinc 2 plus. The copper ions are picking up those electrons to become copper solid. And that's why we see the blue colour of the solution fading over time, because the copper sulfate ions that give the solution its blue colour are disappearing and forming copper solid. To get an overall redox equation, that should say page 12, all we have to do is combine the two equations, and we can do this by cancelling out the electrons on both sides. So we take our two equations, cancel out our electrons, and we end up with the full balanced equation at the bottom. That is called the redox equation. Hopefully all of that is pretty familiar because we have done it in Nat 5 and we've already covered it at higher. So I'm hoping that everybody will be very familiar with that. Let's have a wee practice. So what I want you to do is write me the redox equation for magnesium metal reacting with silver nitrate solution to form silver metal and magnesium nitrate. So exactly the same situation, just two different metals, and the following steps will help. Number one, look up your two metals, magnesium and silver. See which one is above and below. Whichever is above is going to be oxidized. So you're going to write the oxidation equation, which is the equation on page 12 flipped. And then for the lower down metal, you're going to write the reduction equation, which is just as it is on page 12. Once you've written your two equations, you need to balance your electrons. So make sure if you have one electron in an equation and two in the other, you balance them out by multiplying out by 2. And then finally you combine to give the overall redox equation. So pause the video, have a wee go at that, and then unpause and we'll go through how to do that. So first of all, like I said, the magnesium in page 12 of your data booklet is being oxidised. It is above silver, so that means it's going to be oxidised. So we write the equation on page 12 flipped. This ends up with magnesium solid, gives magnesium 2 plus aqueous plus 2 electrons. The silver is below magnesium in the electrochemical series, so that means it's going to be reduced, so we write it as it is. That gives us Ag plus an electron gives Ag solid. So that's the kind of first step to establish what has been oxidised, what's been reduced, and write the equations. The second step is then to write out your equations and check your electrons. As we can see in the magnesium equation, we have 2 electrons, and the silver equation we only have 1. So to fix that, what we need to do is multiply our whole silver equation by 2, and that's what I've done here. The very last step of this then is to cancel out the electrons. Remember, you do not write electrons in a redox equation. So you cancel out your electrons on both sides, write the reactants on the reactant side, write the products on the product side, and that's your full redox equation. So we have Mg plus 2Ag plus gives Mg2 plus 2Ag at the end. You don't have to write your state symbols, but if you do write them, make sure you write them correctly. Another one wee bit then before we go on to our new stuff is to remember oxidizing and reducing agents. So remember, an oxidizing agent causes oxidation, but is actually reduced itself. So it oxidizes everything else, but it gets reduced. And a reducing agent is the opposite. So it causes reduction, so it reduces everything else, but it is oxidized. So if you're looking to find out what the oxidizing and reducing agents are, figure out what is oxidation. So what is being oxidized is a reducing agent, and what is being reduced is an oxidizing agent. So it's just kind of opposites. Here is an example. Again, I want you to tell me what the oxidizing and reducing agents are in this reaction. Pause the video, have a wee go, and then unpause to see what the answers are. So in this equation then, let's start with oxygen. So oxygen is a molecule here. So we have 2 oxygen atoms becoming a 2 minus ion. So for oxygen to go from being neutral to becoming 2 negative, it has to have gained electrons. So oxygen is gaining electrons. That means that oxygen is getting reduced. So it must be the oxidizing agent. Because there are only 2 species in this, that means that the magnesium has to be the reducing agent, which must mean that it gets oxidized. So let's check. So we've got magnesium solid becoming magnesium 2 plus. Yep, that means that it has lost electrons, so it has been oxidized, which means it is the reducing agent. There are 2 slides here with a list of things that you need to know about oxidation and reduction. I thought I'd include this here in case you're going through this video thinking, I can't remember any of this stuff. This is a wee helpful kind of checklist of all the things that you need to know. So if you want to, you can certainly pause the video and jot it down somewhere to refer back to if you want to. Here is the second slide here. This is basically come from the course support notes on the oxidation and reduction section as mandatory knowledge. So everything that you are seeing on both of these slides, you need to know off by heart for your exam. Our new learning then is to use a technique that we've previously explored before in National 5 called titration. But this time, rather than using an acid and a base, we can use a redox titration. So our aim for this experiment is to determine the mass of vitamin C in a vitamin C tablet by carrying out a redox titration using a solution of iodine of accurately known concentration, and we're going to use starch solution as an indicator. So you do need to use an indicator just like you would in acid-base titrations, unless you are using something like potassium permanganate, which is purple and it can be its own indicator. But for your vitamin C and iodine, as you know, the test for starch is to use iodine. That means we can use starch solution to indicate our end point of this titration. So, vitamin C can undergo a redox reaction with iodine, in which the vitamin C is oxidised and iodine molecules are reduced. Now, when you are given questions on this, you will usually be given an equation, and we'll look at that in a wee second. I first of all wanted to draw your attention and just remind you of the different types of glassware and equipment that we use when we are setting up a titration. We have our burette, which has a scale, and your tap. So this is the piece of equipment that you fill with your acid or whatever you're titrating, and use the tap to expel tiny amounts of liquid so that you can reach an accurate end point. Remember, when you fill your burette, you should be filling it at eye level. In other words, you should be looking directly at where you're filling. And you should also make sure that the bottom of the meniscus is just touching the line of where you want it to go. So when you're reading the volume of your burette, you are reading from the bottom of the meniscus, which is just a kind of little semicircle. The conical flask is what we use to usually put our alkali in and our indicator. So we'll have some starch indicator in our conical flask for this titration, and that's just what we use to put underneath the burette. Make sure it's not too far away and that the drops are going straight into your conical flask. Lastly, we have a pipette filler and a pipette. So this is to measure out accurate volumes of solution. So when we are filling our conical flask with whatever's going in there, if you wanted to fill it up with 25 centimetres cubed of your base, then what you would do is use the pipette filler to measure it up to the mark, which is usually around about here, and that is you at an accurate volume of 25 centimetres cubed. You also get pipettes that are like 10 centimetres cubed as well, but that is a piece of equipment used to measure one volume of liquid only. And as you all know, you can use the pipette filler just to draw the liquid up into your pipette. You should fill it above the line first and then lower it down again until that bottom of the meniscus is just sitting on the graduation mark. So here is what it looks like set up. There's a diagram. You would set up a clamp stand to hold your burette in place. You would fill your burette obviously using a funnel, and you should always have a white tile underneath your conical flask so that it will help you better stop your titration as soon as you are past the end point. So as soon as you reach the end point. The method then is a vitamin C tablet was dissolved in 25 centimetres cubed of water and then transferred to a 250 centimetres cubed volumetric flask. So the volumetric flasks, remember, are the flasks with the long necks with a kind of round bottom, and made up to the mark with water. So 25 centimetres cubed of that solution, so it's been diluted, was transferred to the conical flask using a pipette and pipette filler. All glassware was rinsed with their respective solutions before filling. That is something you can do to make your titration more accurate, is in case any of the glassware has been washed and not dried, it might have some kind of drops of water in it. If you rinse the burette with your iodine solution just through once and then fill it up, then that means that there is only iodine solution in your burette. The conical flask contains 25 centimetres cubed of vitamin C and starch. So remember, starch is there because it is the indicator of the end point. So these are just hypothetical results. We have our titer, rough 1, 2, and 3, and volume of iodine used in centimetres cubed. So just like all titrations, we need to come up with an average volume of iodine used. For this experiment, our rough titer is 18.5, which, as you can see, is not concordant with any of the results 1, 2, and 3. You never use your rough titer and your average, you only use concordant results, remember. So that means results within 0.2 centimetres cubed of each other. So if you calculate that average, it ends up being 17.6 centimetres cubed. So when we are using our volume of iodine used, we're going to use 17.6 centimetres cubed. So here is the redox equation. So we have our vitamin C here, being oxidized and our iodine being reduced. So as we know, iodine is a kind of orangey brown colour. So in the burette, we're going to have like an orangey brown solution, and our vitamin C with starch should be a clear solution in our conical flask. Now, when we start titrating these together, the iodine molecules are going to react with the vitamin C molecules to produce these products that you can see on the right hand side. Now, what happens is when there is no vitamin C left, when it's all been oxidized, then we're going to have a surplus or just like an excess of iodine molecules. Now, when these iodine molecules do not have vitamin C to react with, what they do then is they react with the starch in the starch indicator in the conical flask, and you get a colour change from clear to blue or black. This will obviously happen very, very quickly, and that is therefore the end point of this reaction. So as soon as you see the colourless solution going to form a kind of blue, it is kind of like a dark blue colour, then that's the end point of this, and all of our vitamin C has been reacted. So if we have a look at our redox equation, then we've got our vitamin C being oxidized at the top and our iodine being reduced at the bottom. Now, just like any other redox equation, we do need to write it fully by cancelling out the electrons. In this scenario though, we have 2 electrons on either side, so we don't have to do any multiplying or anything. All we do is cancel out our 2 electrons and write the redox equation at the bottom. So this at the bottom here is our full redox equation. And what we're going to do is we're going to use the ratio of moles of vitamin C to iodine to try and calculate the concentration. So from this, we can see that 1 mole of vitamin C reacts with 1 mole of iodine. So it's time to start our kind of calculation now. There have been lots of information that has been labelled in the question. These questions, you'll find out once we start doing them, are very long. You need to kind of go back and forward and make sure you've got the right concentrations, the right volumes and things. So what we are going to try and figure out first is the number of moles of iodine. Then we can work backwards and say, well, if that amount of iodine reacted, that must be the same amount of vitamin C, because they react with each other in a 1-to-1 ratio. So our burette is filled with a 0.031 mole per litre iodine solution. So that's its concentration. Remember, its volume is our average titer, which is 17.5, or whatever the equivalent is in litres. So to get the number of moles of iodine, we're going to do concentration times volume. We have 0.031 that I just showed you as our concentration, and 0.0176 litres for our volume. Remember, volumes must be converted into litres in calculations. That gives us a number of moles of 5.456 times 10 to the 4. Now, the numbers in these redox titrations are usually quite small. So if you get something times 10 to the negative 4 or times 10 to the negative 3, don't worry about it. You can just keep it like that. There's no need to take it out of scientific notation. If you're happy to work with it as that number, then just leave it the way it is. So because we have a 1 mole to 1 mole ratio, 1 mole of vitamin C is reacting with 1 mole of iodine. That means that 5.456 times 10 to the 4 moles of iodine will react with the same number of moles of vitamin C, because we have that 1-to-1 ratio. So now we have a number of moles of vitamin C. We want to then scale up. So if the 25 centimetres cubed that we titrated contains 5.456 times 10 to the negative 4 moles of vitamin C, then that means that the 250 centimetre cubed solution, so that is our standard solution that we made up, contains 10 times that much, which is 5.456 times 10 to the negative 3 moles. So that is the number of moles of vitamin C in a tablet, because we took a tablet, remember, dissolved it in some water just to get it dissolved, and then we put it into a 250 centimetres cubed volumetric flask and filled it up to the mark. So when we find out how many moles are in 250 centimetres cubed, that's how many moles are in one of the tablets that we dissolved. So if we want to work out the mass from that, then what we need to do is number of moles times the gram formula mass. So our number of moles, like we just calculated, is 5.456 times 10 to the negative 3. The gram formula mass of vitamin C you can work out using the formula is 176. So that gives our total mass of vitamin C as 0.96 grams. So our conclusion to that experiment then is a mass of 0.96 grams of vitamin C was determined to be contained in one tablet. Now the questions that you are asked about this are very, very similar. They might be different reactions each time, but the method for solving the calculation part is exactly the same every time you do it. So as long as you follow the steps, you really shouldn't be getting these wrong. It looks very complicated, but if you take each step in turn, then you'll see that it's actually not. It's mainly Nat 5 knowledge of using your triangles with a wee bit of higher thrown in. So what we're going to do now is we're going to go through our questions. As always, please attempt the questions on your own first. If you get stuck, that's fine. Remember, you can unpause the video and go through the answers and make sure that you're self-marking your work as well. These questions have been taken from the 2019 and 2018 paper, so they're very recent questions and they are, like I said, very similar. So, question number 1, the concentration of hypochlorite, now that's the OCl negative ion, in bleach can be determined by a redox reaction that involves 2 steps. So in step 1, you're adding an excess of acidified potassium dichromate to convert the iodide ions into iodine. Step 2, the iodine produced in step 1 is titrated with sodium thiosulfate. It says write the ion electron equation for the reduction reaction taking place in step 1. Now this is tricky because most people will look at that and say, right, I need to find out which species is above the other in the electrochemical series. That'll tell me what's oxidation, that'll tell me what is reduction. You would be absolutely correct to do that, but the problem is that the hypochlorite ion is not found in the data booklet. So what we have to do is we have to use a little bit of our knowledge of writing complex ion electron equations to solve this. Now let's start by kind of looking and seeing which species is most likely going to be reduced. Our 2 iodine, so our 2I negative, is becoming I2. That means that it is losing electrons, so that's oxidation. So we're going to ignore the iodine. As always, our 2H plus ions are becoming water. We don't really kind of count that just as a rule of thumb as oxidation or reduction. So what we're left with is our hypochlorite ion and our chloride ion on the other side. And that's what we're going to start with. We're going to start with our hypochlorite ion on the left and our chloride ion on the right. Now we know a method of balancing this equation on both sides, and we're going to go through that method right now. So we have our hypochlorite ion on the left and our chloride ion on the right hand side. Now to balance this, we first need to balance the oxygen atom because our main element, which is chlorine, is already balanced. We have one on each side. So to balance the oxygen out, what we're going to have to do is add a water molecule to the right hand side, which is H2O. Now we have an excess of 2 hydrogens. So on the left, we need to put 2 hydrogens, and we do that by putting 2 hydrogen ions, so 2H plus. Our charges on each side are the same right now, it's -1 and -1. Because we've just added 2 positive charges to the left-hand side, we can balance that out by adding 2 electrons. So your whole ion electron equation ends up becoming this. 2H plus 2 electrons plus your hypochlorite ion gives the chloride ion and a water molecule on the right hand side. Part 2 of this question is asking a 25 centimetres cubed sample of diluted bleach was transferred into a conical flask and excess acidified potassium iodide was added. Remember, the potassium iodide is added to make the iodide ions into iodine. The iodine produced was titrated with 0.098 moles per litre of sodium thiosulfate, requiring an average volume of 9 centimetres cubed to reach the end point. We're being asked to calculate the concentration in moles per litre of the sodium hypochlorite in the diluted bleach. So even though there's two stages to this process, we can think of the iodine, the number of moles of iodine, to be the same as the number of moles of hypochlorite, because we're using the hypochlorite to iodine to titrate the iodine against sodium thiosulfate. So what is step one in this reaction? We need to look at the equation and first of all establish our mole ratio. So 1 mole of iodine will react with 2 moles of sodium thiosulfate. So I've just gotten that from here. 1 mole of iodine, 2 moles of sodium thiosulfate. Now to find out the number of moles of sodium thiosulfate, we can do concentration times volume. Our concentration given in the question is 0.098 mole per litre. And our average volume of the titer is 9 centimetres cubed, which of course we have to transfer into litres, which gives it 0.009 litres. Our number of moles of sodium thiosulfate is therefore 8.82 times 10 to the negative 4. So if we work backwards, how many moles of iodine is going to react with that? Well, it's going to be half the amount because we have a 2 to 1 mole ratio. So if we half 8.82 times 10 to the negative 4, we get 4.41 times 10 to the negative 4 moles. Remember, this is our moles of iodine slash our moles of the hypochlorite ion. Our concentration is going to be number of moles divided by volume. So we've got our number of moles, we've got our volume. Our volume in the question is 25 centimetres cubed. So if we have 4.41 times 10 to the negative 4, remember, put your volume into litres, we have 0.025. That is going to equal 1.76 times 10 to the negative 2 moles per litre. Now, obviously, you would get multiple marks for this question. You would get a mark for calculating correctly the number of moles of sodium thiosulfate. You would get a mark for saying the number of moles of iodine is therefore 4.41 times 10 to the negative 4, which is the same as the number of moles of hypochlorite. And then one for your final answer, which is 1.76 times 10 to the negative 2, moles per litre, because we've got a concentration. So this is the exact same steps as we took before. The only difference is in our experiment example, we were looking for a mass, which just requires that kind of extra step of looking to see how many moles you have in your diluted solution. Whereas this is just figuring out the concentration. So this question is probably a wee bit easier just because it doesn't include that step. Okay, so that's the first question. Second question, iodine is required for a healthy diet. You see what I mean about these questions being quite long. They require a lot of reading, and that's one of the challenges, is to pull out all of the information that you're requiring for the question. So food grown in certain parts of the world is low in iodine. To prevent iodine deficiency in people's diets, table salt can be iodized by the addition of very small quantities of potassium iodide, which is Ki. The number of moles of iodide in a sample of salt can be determined by the following procedure. So step one is to prepare a standard salt solution by dissolving an accurately weighed sample of iodized salt, so 50 grams, in water to give a final volume of 250 centimetres cubed. Step two is to transfer 50 centimetres cubed of the salt solution to a conical flask and add excess bromine solution to convert the iodide ions to iodine. Step 3 is to titrate the iodine released with sodium thiosulfate solution. And A is asking us to describe a procedure to accurately weigh out 50 grams of a sample of iodized table salt. So whenever we are trying to weigh something accurately. So, like the vitamin C tablet in our experiment, or this sample of iodized table salt, we are going to weigh using the tare function of balance. Now, most people will have absolutely done this before. If you are baking or tracking food on MyFitnessPal or whatever you want to use, the way to do this is always the same. If we're baking a cake and we want to weigh out 200 grams of flour, most people will get their balance, put the bowl onto their balance, zero it, and then just add your flour until you get to 200. And that means that you have 200 grams of flour. Now, in chemistry, the weighing procedure is exactly the same. If we want to accurately weigh out 50 grams of this table salt, all we're going to do is get an accurate balance, put a little plastic weighing boat onto the balance, use the tare function to zero the balance, and then start adding the salt until we get to 50 grams exactly. So describing that procedure of using the tare function will get you the mark for that question. B, the overall equation for the reaction of bromine solution with iodide ions is shown, so you've got that there. Write the ion equation for the oxidation reaction. So oxidation is loss from oil rig, so we want to write down the part that is losing electrons. There's two ways you could do this. You could say, right, we've got iodine and bromine. You could look those two things up in the electrochemical series. You will find that iodine is above bromine, so it must be oxidation. And then you would write it out flipped. So it would be 2I aqueous, arrow I2 plus 2E negative. So that's one way of doing it. The other way of doing it is just simply to look and say that you have two iodide ions, which are negatively charged, becoming an I2 molecule. So we've got two extra negative charges here we need to get rid of. So you've got 2I negative aqueous is going to give away 2 electrons, and then you'll have your iodine molecule on the other side as well. So that's what that looks like. It's up to you if you want to. I would always check it with the data booklet anyway, so if you prefer the data booklet method, then feel free. Just remember, when you come across something that isn't in the data booklet, that's when you need to use your balancing steps to balance all the atoms and the charges on both sides. So see, we have 3 samples were prepared as described in step 2. Each sample was titrated with 0.001 moles per litre sodium thiosulfate solution, and the results are shown below. So we have a table here with our results in it, 3 samples and the volume of sodium thiosulfate. It's asking us to calculate the average volume in centimetres cubed of sodium thiosulfate solution that should be used to determine the number of moles of iodine released. Now again, these are quite common questions. Let's have a look at the table. We have 3 different volumes. Only samples 2 and 3 are concordant though, so we would ignore sample 1 and only average 2 and 3. If we do that, we get 9.4 plus 9.6 divided by 2, which gives us 9.5 centimetres cubed. And part 2 is calculate the number of moles of iodine released from 50 centimetres cubed of the standard salt solution. So this time we're not being asked to go the extra step and calculate the concentration or anything like that. We're only being asked to calculate the number of moles of iodine. So this question is broken down where each part of the question is a different step to the main calculation. Sometimes they can be asked like that, or like the first question we did, they can just be asked all in a winner, and you need to go back and find all of the information and do all the steps yourself. So the number of moles of iodine released from 50 centimetres cubed of the standard salt solution. Again, first of all, let's establish our mole ratio. We have 1 mole of iodine reacts with 2 moles of sodium thiosulfate. We can calculate our number of moles of sodium thiosulfate. On the slide before, it showed us the concentration is 0.001. Our volume that we just calculated was 9.5 centimetres cubed. So in litres, that is 0.0095. And the number of moles of sodium thiosulfate, therefore, is 9.5 times 10 to the negative 6 moles. From that, if we want to get our number of moles of iodine that has reacted, then as we can see, we have a 2 to 1 mole ratio. So all we have to do is half that number. So 9.5 times 10 to the 6 divided by 2 is 4.75 times 10 to the negative 6 moles. So this calculation is a little bit easier than the first one just because it's broken down into stages and you can do one part of it at a time. So that is the end of the redox titration lesson. Hopefully you understand the process of accurate volumetric analysis. So by that I'm talking about making standard solutions. So remember, a standard solution is a solution with accurately known concentration. So you need to be very, very accurate with your weighing. Make sure that you're using appropriate methods like weighing by difference or using the tare function to weigh out your masses of solid, dissolving this in some water to then place in a volumetric flask. Make sure that you're rinsing the beaker a few times to make sure that any particles still stuck in the beaker are being transferred over and not being left behind. And being really, really accurate in the way that you fill your glassware to the mark. So again, we talked about the meniscus. The bottom of the meniscus needs to be sitting on the line. So as long as you are aware of all of those different practices, then you are understanding the process of accurate volumetric analysis. We also want you to be able to perform these titration calculations. Now, this is another thing that you will get much better at the more you practice. So we've only had 2 examples here on this video. On our next live lesson, we will do another 4 examples, and I've also got some extra examples for you to practice if you need to. Hopefully that's been helpful for anybody, and as always, if you have any questions about the lesson content or any of your tasks for this week, just give your teacher a message on Google Classroom. Have a good week.